Buddy, I'm going to give the second half of Friday's lecture. Again, I will be gone on Monday the 24th, and so this fills in that lecture so you can get started on the camera transform project. I debated whether to do review. I typically lead each lecture with review, and I thought I might review the derivation of the camera transform, but I kind of went fast for a reason. I wanted you to get a feel for it. I don't really want to bog down in the math, and so instead I decided to just promote Ken Joy's website. If I go back, this is Ken Joy's graphics notes, and if you click on the graphics notes, there is a camera transformation. You'll see I've actually in my slides put in some screenshots from the camera from this web page, and then if you go to the bottom, and I'm sure there's other ways to access this, there's actually the view transform as well. So here's all the stuff. They had a link up there for what Kramer's rule was and so on, and here's the stuff on the view transformation. And I'll tell you right now, I'm actually not going to derive the view transformation. I'm just going to recommend that you look at that web page. So let's dig in. We left off on solving the camera transform with Kramer's rule, and so now we're going to look at the view transform. So summarizing where we started by doing the simplest matrix, which was from image space to this device space, or our weird hybrid of device space that involves the Z buffer. And then on Friday, we derived the matrix that takes you from world space to camera space, which is called the camera transform. And now we're doing the transform that takes us from camera space to image space, which is called the view transform. So we've seen this picture on the left before, talking about the view frustum. Again, with the camera frame, the camera will be here at the origin, and the z-axis will be looking away from the focal point, which is between the near plane and the far plane. I do want to clear up something that may be a point of confusion. We talked about homogeneous coordinates and that we'd have an x, y, z, w, and then we'd want to divide by w. This w here is a different w. This is a u, v, w vector bases, and so I had referred to these as v1, v2, v3 in my slide. So please don't confuse this w, which is the third basis of the vector, with the w we're dividing by in the homogeneous coordinates. Anyway, this here is the view frustum, and so this is a three-dimensional view on the left, and on the right is a cross-section of the view frustum, and so you can see all the same elements, that there's a near plane that's n units away, there's a far plane that's f units away, and that there is a view angle, and again a very wide angle would lead to a fisheye view, and that w, the z-axis, is pointing away from the focal point. So we've already talked about this before, that this is where we get our perspective transformations. And so here on the left we have our view frustum, and on the right we have a cross-section of the image space cube. So we're not looking at the u-axis. Notice I also now have switched to use Ken's notation, where I have a v and a w. And as we apply the view transformation, we're going to again make this perspective transformation where things that are closer get bigger and things that are further away get smaller. And so I'm asserting here this is not a combination of translations and rotations and scales. It's more complex, and this is one of those spots where homogeneous coordinates pays off for us. And so here we're showing a mapping from the view frustum to the image space cube, and so the front left and the by the near plane, or sorry, bottom whatever. This corner right here maps to v minus 1, w minus 1, and the back corner maps to v minus 1, w plus 1, and similarly with the ones on the top. And so this near plane is being stretched out, and I guess it looks like the far plane's a little bit bigger too. Of course, what do the scales really mean? But the point is the near plane is becoming the same size as the far plane, at least the portion that intersects the pyramid of the view direction that makes this so-called view frustum. And so if we have an object within our view frustum, then that object is going to get distorted so that the part that's clearer gets bigger, a part that's nearer gets bigger, and the part that's farther away gets smaller. Okay, so again, I already said this. I'm not going to derive the viewing transformation. I don't think it's a use of class time. And although I don't think people have bought the Ed Angel book and they're not using that textbook, Ken's notes are free. They're on the web. They're fantastic. And so there is the link for deriving this. And if you want to copy and paste this from the PowerPoint, keep in mind that it would often put a space in the link name. So if you see any %20s, that's how web browsers do spaces and take those %20s out. Okay, so here is the view transformation. This is what we didn't derive. And so the input to the view transformation is a view angle alpha. Again, a big value would be a fisheye view, a near plane, and a far plane. And that's all we need to know because we're assuming at this point that we're in the camera frame. So the camera is sitting at the origin and the camera is looking down the z-axis. So this transform, again, it transforms the view frustum to the image space cube, and it's bounded by the viewing pyramid and the plane z equals minus n and z equals minus f. So we're looking down the negative z-axis, and if we go n units down the negative z-axis, we'd get to z equals minus n. Going f units down the negative z-axis takes us to z equals minus f. And we've already talked about image space and how its bounds are from -1 to 1 in u, v, and w. So this is the image space cube, and so it has along the diagonal cotangent of the angle over 2, and then the relationships in this bottom right quadrant have to do with the near and far plane. And you'll notice for the first time we don't have a 1 in the bottom right, and so that's how we're going to start getting these values with w not equal to 1. And when I say w, I don't mean UVW, I mean in the previous slides where it said XYZ W. I'll also just note for those who are implementing it, which is of course everyone, be careful as you are dealing with the math functions in C. I think by default they're in radians, and I can't remember right now if the project's in degrees or not. But you may have a problem if you don't convert to radians, so keep that issue in mind. Okay, so let's do an example. So here's our example. Our input parameters are a 90-degree angle. The near plane is 5 units away and the far plane is 10 units away. This picture doesn't really seem to match that. If I had to really guess on the picture, I'd say the angle is 60 degrees, but we're going to pretend it's 90 because I like the math better with 90. And it actually looks like the near plane, this length here is not equidistant to that length, and so is this really 5 units and is that really 10 units? Well, use your imagination. And so then this matrix here, if we have these this angle and the near plane and the far plane, becomes this matrix here, 1, 1, 3, 20, and -1, and the rest zeros. So this matrix would take us from the camera frame to from camera space to image space. And if we had geometry in world space and we combine this matrix with the camera transform, then we'd be able to take geometry from world space to image space. And if we combined it with the third matrix that we did, we'd be able to take the composition of these three matrices together from world space to device space. So let's multiply some points. So here's the points 0, 7, -6, 1, and 0, 7, -8, 1. And so as we apply these 2 points, the first point gets transformed to be 0, 7, -2, 6. So of course we have a w value that's not 1. And so we would divide by 6 and get 0, 1.16, -0.33. And if we do it with 0, 7, -8, 1, then we get 0, 7, 4, 8. And as we divide by 8, we get 0, 0.88, 0.5. And so this would mean that it's in the image space, x equals 0, y equals 0.88, and z equals 0.5. So good. So you can see right away this one is outside the image space cube and this one is inside the image space cube. And if I remember my slides right, we're going to see, we're not seeing a visualization of this. I guess it'll be our following slide. And so that's because we have a 45-degree angle, and so anything where it is the y is less than the z is inside, and anything where y is bigger than the z is outside this 45-degree angle, the line y equals z. So here's some more points following that same idea: 0, 7, -4, 0, 7, -5, all the way up to 0, 7, -11. And so as we get to, for example, -11, we're outside the far plane, and so we end up at z equals 1.18. as we get to minus 10, we end up right on the plane z equals 1. And as we get to z equals minus 4, we are well inside this. If we get to z equals minus 5, we're at minus 1, so that's inside the image space cube. Interestingly, if we get to minus 4, we're well inside. So here a unit beyond the far plane led to a little bit beyond z in the image space, but here a unit inside the near plane led to dramatically outside the image space cube, and we'll talk more about that before. By the way, you'll see that our math is changing, and if I remember the prompt correctly, we are going to have to change our z-buffer calculations. It looks like minus 1 is the front of the z-buffer cube here, and plus 1 is the outside of the z-buffer cube. And again, so that's how this particular transform works, and again, I think you're going to have to modify your z-buffer calculations. So again, here was our slide that showed the perspective changes that happened to our cube and how the view frustum transformed into image space. And then I think now is my visualization where I put in the points. And so here are the points that we plotted and discussed before. And so the one that's at z equals minus 11 ends up outside the image space cube. The one that's at, right on the far plane ends up right on the image space cube, inside. And then this one that's outside the line y equals z ends up outside because its y is too big, and this makes sense, right? That right here is the edge of the peripheral vision of the viewer, and this is outside the edge, so it's outside the image space cube. And this one that's on the near plane continues to be on the near plane, but still outside of the view of the observer. And then this one ends up being really far out, and so there's this nonlinear relationship between where you are with respect to the near plane and the far plane and how you get mapped into image space. And so actually the halfway point here between the near and far does not get put at the halfway point between the near plane and the far plane. It actually gets put much further back, and things that are closer to the near plane get more resolution in this transformation. Good, and that's what it said. Note there's a nonlinear relationship in Z. So let's put it all together. And this is not put it all together for the view transform. This is for everything we've been lecturing on for the last week. You're going to take a camera C, you're going to calculate a camera frame, and then once you have a camera frame, you can calculate the camera transform. You're going to calculate the view transform, which we didn't go into much depth. I just put the formula up, and you can check out Ken Joy's notes if you want to know the derivation. You calculate the device transform. That's the one that does the three spaces along the bottom row all in one. That was the really simple transformation that had the scaling x prime, y prime, z prime. We're going to compose these three matrices into a single matrix, M, and then for every triangle, we're going to apply M to each vertex of the triangle. And once we do that, we've taken our triangle that's in world space, we put it in device space, and then we can apply rasterization and z-buffer stuff. And it says Phong shading. That's wrong. I wish I would have changed that slide. We're going to actually do Phong shading earlier, but we can call the code that we have before once it's in device space. Okay, so let's talk about Project 1F. So it's due on Sunday the 30th. The goal is to add arbitrary camera positions. You're going to extend your Project 1E code. You're going to reuse the same geometry we've had before. We're going to reuse the reader, going to reuse the shading stuff. There's, again, no CMake or Project 1F.cxx. You're just going to make a Project 1F.cxx and you're going to update your CMake. What is new is there's a matrix.cxx and there's a camera.cxx. You can thank my mentor Ken Joy for the matrix. He said students always get caught up on the matrix and you're just better off handing them code, and so that's what I do. So matrix.cxx is complete. There are some methods. There's a transform point method. There's some compose matrices methods, and you can print the matrix. And I encourage you to print the matrix. I'd encourage you to build your intuition. I'd encourage you to, for example, take some of the transforms we have and send in input points and get out output points, and just make sure that it's doing what you think it's doing. I think it'd be a real mistake to try to implement everything and then run it and have it not work and then have to figure out what's gone wrong. Every time you have a chance that you can test something, I encourage you to do so. Camera.cxx, you're going to work on this. I'm giving you the data members, but you'll need to build the view transform, the camera transform, and the device transform, and you'll probably want something to set up the camera frame as well. Also, there is a function called get camera, and I give that to you. You can say how many frames you'd like, and then which specific frame you want. So if you call get camera 0 1000, it gives you the first frame. If you call get frame 1 1000, it gives you something that's 1,000th of the way through the camera path. 2 1,000th would be 2 1,000ths of the way through the camera path, and so on. So I've implemented that for you, and it's a way you can generate a bunch of camera positions. What do I want from you? I do not require you to make a movie, but I would like you to get out 4 images. So at 0, 250, 500, and 750. If you want, go do 1,000 images and make a movie. I encourage you to do that. Put it on your website. I think this is a very significant project. I think you should all feel really proud when you complete it, and put the movie on your personal web page for employers or something like that. It says here it says can discuss how to make a movie if there's time. I like using FFmpeg. I'm hoping someone who also knows how to use FFmpeg will just post to Piazza. If not, I can do that when I get back from my trip. So here's the game plan and code. This is the same get triangles routine that we've been using, an allocate screen, which sets up the screen, a for loop over the 1,000 cameras. This is very important. Initialize the screen, because you don't want it to be that you deposit into the screen object and then you re-render into the same screen object for the second render and so on, and you've got old colors and old Z buffers in there. You need to clear out the black and set the Z values each and every render. Then you'll get the camera, that's just calling my stuff, and then you need to transform the triangles to device space, and this means you have to set up the matrices based on the camera and apply them to the triangles. And by the way, if you modify the vector of triangles, you got to undo it later. I do not want you to just run your program 4 times with 0, 250, 500, 750. I want you to initialize. I want you to be able to do this multiple times. And then once you've done that, then you'll call your existing render triangles routine and you'll save an image, and that's the high-level loop. Here are some answers for get camera 1,000, so you can see what my camera frame is, what my camera transform is, and what my view transform is. And then I think that I've actually put in some points here. I think these points are to prove that I've done it right. I think this is right, the point in the center of the near plane and the center of the far plane, you can see is transformed to the correct locations. So those are my answers for what I did for get camera 0, 1000. Here are some pitfalls. All the vertex multiplications use 4-dimensional points, so make sure you send in a 4D point. Do not send in a double array of size 3, because it's just going to write past the end of it. Make sure your double arrays are of size 4, and when you get it back, make sure the output is of size 4. When you get back, divide by W. Your Phong lighting assumed a view of 0, 0, minus 1. The view will now be changing with each render, and you incorporate that view direction into your rendering. I'm going to talk more about this point. I wish I would have pulled that bullet out, so hang with me and we'll talk more about that. Another point, people often get a matrix confused with its transposed. Again, print, make sure that things are what you expect. The points here are left multiplied, not right multiplied. I think that reflects most of the slides. And again, with multiple renderings, don't forget to initialize the screen, and if you modify the triangle in place, then don't forget to switch it back at the end. Okay, that's old. It's due October 30th. No one should tell me they think it's due November 5th. Due October 30th. I pressed forward, but we didn't get it. There we go, making a movie. Again, FFmpeg, and someone posted how to. Shading, okay. So for 1E, we used the view direction 0, 0, minus 1. For 1F, we're going to do it right. And what that means is, prior to doing our transform, prior to actually applying the matrix to every triangle, you can actually calculate the view direction. So it's the triangle vertex minus the camera position. And then once you have that view direction and you have a normal, you can call calculate shading with the correct view direction. And then you can add a new data member to your triangle, which is the shading value. And then you can lerp that shading value across a scan line. And so, so this should be great, and actually it should take care of some of the normals issues we ran into in 1E. So this is a change you did in 1E, shading in device space. Now you're going to be doing your shading in world space, and associating a shading attribute on the triangle and lerping it as you do your scan line. And it will actually give a more accurate answer. 0, 0, minus 1 was a very good surrogate, but you'll get a slightly better answer doing it this way. And that is it. So thanks for watching this lecture. I hope you find it helpful. I am headed off to Baltimore tomorrow, and it'll be tough to get in touch with me. But I'm hoping people will crank on 1E, and then when I get back on Wednesday, we're going to be figuring out 1E issues, and I can answer 1F issues. So good luck, everybody, and I'll see you on Wednesday. And a final reminder that on Monday, I will not be there, but there's an office hour, and Dan Lee will be there, and she can help run a session between you all, helping each other, and she can help you all. So that's it.